Hello and welcome. In the last video, a couple of weeks ago, I repaired the Sound Blaster 16 sound card, and if you saw that, you maybe remember that I had to put back the CT1748 ASP chip to get the digital sound. Since there are other revisions of the sound card which work without the ASP, I assumed it would be optional. I also made a wrong assumption that the detection logic on the other cards could be in the firmware, but I was pointed out to be wrong by many mindful viewers. The solution is much more simple. As you see, this card, which I also showed in the last video, has no ASP chip soldered, but this card has two jumpers which are responsible for the ASP chip selection. I actually should know it, but unfortunately I must have forgotten those existence. Anyway, this card doesn't have the two required jumpers, which should be closed in case the ASP chip is missing. So let me add the jumpers and check it once again. So the jumpers are soldered and set. Now let's remove the ASP chip and see if the digital sound is still working.
0, 0, 0, 0, 0, 0.
And everything works great. So the solution was indeed as simple as that. Just two missing jumpers and the ASP chip is not needed anymore. Thanks on all the viewers for the hint. I'm glad that this mystery could be resolved. Now, why I also mentioned this card today is because in the last video I soldered the PLCC SMD socket and got some questions about how I did this. Soldering such sockets can be indeed sometimes quite tricky, so let's talk about that a little bit. This topic comes also handy for me because I have something on my to-do list for a while already. I bought this Harris 286 CPU from China a very long time ago and it looks pretty fake to me, to be honest. I didn't test it in all that time, but as I said, it was on my to-do list. The CPU should be a 25 MHz 286. It looks new, but the inscription and the way how it is made doesn't look authentic. If I search for photos of such a CPU, I find images with white paint inscriptions, bigger and using other fonts, unlike on the exemplar which I got with a laser-made inscription. Fake chips are sometimes painted and can be disguised by rubbing off the paint with some alcohol and a cloth. But this chip seems not to be painted. I might be wrong and maybe later revisions looked like this. This chip at least tells to be manufactured in the 31st week of 1997, but as I said, I don't really trust the inscription. I guess there is eventually only one way how to test it if this is a fake or working chip, and today I would like to check it from my to-do list. Here I have a 2T6 mainboard which has a CPU soldered directly to the board. This is a 16 MHz AMD CPU in PLCC68 package. As you see, there is no socket, so I can't just pull out the CPU and insert another one. I use this board often as my 286 test platform and it would be nice to make it more flexible, so I could experiment with other chips. That's why today I'm going to add an SMD PLCC68 socket. First of all, of course, the CPU has to be removed. I use some painter tape and Kapton tape on top to protect other parts around from overheating. The CPU has its die in the center, so I put also some tape in there to protect it from direct heat. Okay, the CPU is removed and I cleaned the PCB with some alcohol. It is now ready to receive a new socket. On this board there are unfortunately no alignment holes, so the socket has to be aligned visually, but that is quite often the case. And of course it is important to maintain the proper orientation of the socket if you don't want to insert the CPU the wrong way around later. Now to the soldering. There are multiple ways how this can be done. As you see on the bottom of the socket there is a plane with holes around where you can go through with a thin solder tip to solder the pins. With a microscope and a steady hand this is a doable operation. Second way to do it is to cut out the base plate completely using such a wire cutter. This way the pins would be easily accessible and the soldering is a child's play. However, the base plate gives the socket the required stability, and when used with bigger chips like this one, especially where you plan to pull and replace the chips more often, you risk to rip off the contacts from the PCB. That's why I don't suggest to use that method, even if it's the easiest one. Instead, today I would like to show a third method which I usually use. It is not the easiest one and I needed to practice a little bit, but it doesn't damage the sockets and works very well for me. When the manufacturers solder such sockets, they usually don't do it manually. Most of the SMD parts are soldered automatically using solder paste like this one. I already showed it in my videos. For example, as I built my socket 7 voltage regulator module project. This solder paste has a slightly lower melting temperature at around 183 degrees Celsius. This is important because the plastic of the socket can stand temperatures between 250 to 290 degrees Celsius. So the trick is to solder the socket in such a way that the solder melts before the plastic does. For this whole operation I don't really need a microscope. It is useful, but you don't need it. However, for the sake of better presentation, I will use it in this video. First of all, I apply the solder paste to the solder pads. Unfortunately, I have no stencil, so I have to do it manually like this. The amount of solder paste is important and probably the most tricky part. Too little and the pins will not be soldered, too much and you risk shorted pins. Unfortunately, this is a question of experience, but probably it's better to put a little bit more than too little. It is not critical if the solder paste from pads near each other touches. It will be later pulled towards the pins when heated anyway, but you can go with a toothpick once between the pads to remove exceeding solder paste. Once solder paste is applied, it is time to align the socket. As I previously said, this board has no alignment holes, so the according standoffs on the socket have to be cut off. Once again, keep the orientation of the socket in mind and align the pins with the pads as good as you can. The solder paste is a bit sticky, so it will keep the socket in place. Now it's time to solder the socket using a hot air gun. As I said, the plastic socket stands temperatures between 250 to 290 degrees Celsius, so I set the heat gun to 270 degrees Celsius. If you see during soldering that the plastic gets glassy, reduce the temperature or move the heat gun further away. Once again, this is a matter of practice. As I said, microscope is helpful but not necessary. If you have good eyes, you can see the solder melting and running towards the pins even with a naked eye. So I go over the full perimeter of the socket and solder the pin section for section. As you see, the solder flows in the first seconds in all directions, but when the pads and the pins are getting hot enough, the solder paste is magically pulled towards the joints. Important there is to check that there are no bridges between the pins. Sometimes it is hard to see because the pins could be shorted under the socket, especially if too much solder has been used. That's why after soldering I always go through the pins one by one and check that the pins next to each other are not shorted. And here it looks good. Now let's put back the original CPU once again to check if all the pins get soldered properly and the system posts. And we have a survivor. the numbers on the post analyzer are running. That means that the CPU is still alive and properly connected. Let's briefly boot into DOS, just to be sure. Okay, that worked fine. The socket installation was successful, and now comes the moment of truth. The whole effort was to be able to test that suspicious Harris CPU in this board. And would you look at that, it is actually working. We have some numbers running on the post analyzer. That's great news, and I totally didn't expect that. I thought this would be a complete fake. Though this could be still a fake, and not a 25 MHz CPU, but at least this is a working 286 CPU. So the socket installation was a success and the CPU is working. Let's get a step forward. This mainboard is designed to work with 12 and 16 MHz CPUs. There is even a jumper on the board which is hardwired to 16 MHz, of course, because previously the CPU was soldered. On the Retro app, this board is even marked to support up to 20 MHz CPUs, and I would like to test this. For this, I will not only have to add a jumper, but also a socket for the crystal oscillator which generates the CPU clock. There is actually a place for another crystal oscillator which is meant to be used for the coprocessor, a floating point unit or short FPU, but this is a story for another video. However, I still think to add also a socket here because I would like to experiment with an FPU as well. So the sockets are installed. I also added some parts and a jumper which are FPU related and will not be part of this video. However, I added this jumper as well, which shows a selection between 12 and 16 MHz CPUs. I don't really know what this jumper is exactly for, since it is also not mentioned in any way in the documentation which is available on the Retro web. Anyway, maybe we will need it later. So here I have 3 crystal oscillators. The CPU needs double clocked oscillators. To run the CPU at 16 MHz, we would need 32 MHz crystal oscillator. With 40 MHz oscillator, the CPU would run at 20 MHz, and with 50 MHz oscillator, the CPU would run at 25 MHz. I already made a video about a 386SX overclocking long time ago, where I explained how it works. Now I will basically try the same. By the way, here I also have a 24 MHz crystal oscillator, which would make the CPU to run at 12 MHz effectively. First of all, let's put back the original 16 MHz CPU and see if everything is still working. Yes, the memory is counting and I see an image on the display. Nice. Now let's briefly try to run the CPU at 12 MHz using this 24 MHz crystal oscillator. It runs, but the memory is counted much slower, as you probably hear. Let's try to set the jumper to 12 MHz and see what happens. Now the board doesn't even post. This sounds like a memory error. Let's try the 32 MHz oscillator again. Same issue. The board doesn't post at all if the jumper is set to 12 MHz. As I said, it is actually undocumented and I have no clue what this jumper means. Error code 10 means ready to start 64 kilobyte base memory test on AMI BIOS. Well, whatever. The jumper has probably to be left in a factory position to work properly. Good. The CPU works at 12 and 16 MHz. Now let's try to ramp it up a bit and go with the 40 MHz oscillator, which should make the CPU run at 20 MHz. Okay, the system posts. Let's see if it's stable. Nope, as I tried to set up the camera, the system froze. I tried a couple of times and mostly it doesn't even post completely. Sometimes it even tries to boot into DOS, but I get different errors trying to get into the operation system. So this CPU or mainboard doesn't run at 20 MHz. That's clear. Just for the science, let's see what happens if I put the 50 MHz crystal oscillator. Theoretically, that should overclock the CPU to 25 MHz. Nope. Now it shows no signs of life whatsoever. Okay, now I again inserted the Harry CPU. It tells that it is a 25 MHz version. Let's see. I don't trust its claims, but let's try to run this one at 20 MHz using a 40 MHz oscillator first. Wow, and the system posts and boots into DOS. This is already a better result than the 16 MHz AMD CPU. So this Harry CPU is at least 20 MHz capable. Now let's try to get it to 25 MHz. No, it doesn't post. It shows some signs of life, but it doesn't post. Let me reset it a couple of times. Maybe we will get somewhere. No, seems to freeze during the initialization. Now the 1 million question, is it the CPU which is fake and doesn't run at 25 MHz, or is it the mainboard? On the RetroWeb, once again, the entry mentions a maximum of 20 MHz, so maybe it is the board which doesn't stand those 25 MHz, even if the CPU would. Unfortunately, currently I can't answer this question. But what I can do is to compare the speed and show you some numbers. Here are some benchmark results which I made at 16 and 20 MHz. I also added the results from a 386SX system to compare it clock for clock. There is something about it what felt like a scam back in the days. As you see, the results on the 386SX are a bit slower, and this is what I measured already on various 386SX versus 286 benchmarks. But why is the question? You see, a 386SX is more or less a 286 in disguise. It supports 386 features, but unlike a real 386, which is also called 386DX, the SX version has only a 16-bit memory bus and no cache. Just like a 286. 386SX just can run software which was written for a 386, but for all the software which runs on a 286 too, a 386SX delivers worse performance clock for clock compared to a 286. I never investigated why exactly, but I think that because 386SX is a 32-bit CPU internally, it needs 2 cycles to write to a 16-bit memory bus, where a 16-bit 286 needs just 1, and so has less overhead during the operation. That, however, is just an educated guess, and I'd be glad to hear from you why you think 386SX loses against a 286 clock for clock. Also, imagine you pay a fortune and buy a 386 computer to upgrade your dated 286 back then, and it turns out to be a 386SX which runs every program slower which you were using on your 286 previously. That felt like a real scam, since that tiny difference between SX and DX was of course not proudly explained in the commercials. Anyway, benchmarks were not planned to be a part of today's video. It should be more about how to solder an SMD socket, and I think this was a success. I was also quite surprised to see the CPU actually working. As I got it, my first thought was that it is definitely a fake. Well, sometimes we lose and sometimes we win, right? I hope you enjoyed this video, thank you for watching and goodbye.